Welcome. This is Zhou from the University of Chicago, and today I'm presenting the effect of natural language explanations on out-of-distribution generalization in few-shot NLI. This is joint work with Chenhao at the Chicago Human Plus AI Lab. While pre-trained language models can achieve great performance on benchmark datasets in natural language inference, they cannot really generalize well out of distribution. In this paper, we're interested in whether explanations can help model learn this task better. We look at this problem in a few-shot learning setup and evaluate the models both in distribution and out of distribution. One contribution of our work is the construction of an explanation dataset called eHands. We annotated explanation templates for the original Hands dataset. An example premise is the artist was offended by the dancer. A hypothesis is the dancer offended the artist, and the explanation we provided is offended is the active form of was offended by. So we swapped the order of dancer and artist. If you think about it, it's actually non-trivial to come up with natural language explanations for a task that is very intuitive, such as NLI. We tried our best to make this dataset high quality, so please check it out at this link below. In our experiments, we used a few-shot learning setup. We built a few examples for each template in training and evaluated the results using 5-fold cross-validation on the templates. Therefore, we train on 80% of the templates and test on either the same templates or the other 20% depending on whether we want to do in-distribution or out-of-distribution evaluation. Besides the effect of on-scene templates, we're also interested in the impact of on-scene vocabulary. Thus, we came up with these 4 test categories. Similar to the split in templates, we divide the vocabulary into 2 sets. One is used in training and in-domain vocab test sets, and the other is used in out-of-domain vocab test sets. Our models use an explain then predict framework. An explanation is first generated given an NLI input, and then a label is predicted based on both the generated explanation and the original input. We have multiple baselines, including one where the models does not use explanations for learning, and we name it as the label-only baseline. We're also interested in the effect of pre-training on other explanation datasets, so we have a model pre-trained on ESNLI. We find that models can generate explanations with very high BLEU scores against the ground truth explanations. The figures show how BLEU scores steadily increase as we increase training size. The solid lines are IND vocab, and the dashed lines are for OOD vocab. The left 2 figures are for IND templates, and the right 2 figures are for OOD templates. While the OOD test performances are lower than those of IND, we observe pre-training on ESNLI helps mitigate their difference. Overall, the BLEU scores are high. IND vocab IND template achieves BLEU scores above 90, and even the most challenging test scenario achieves a BLEU score at around 20. Given these high BLEU scores, we were surprised to find that learning with explanations does not help label prediction. The figures here show prediction accuracy as training size varies. The yellow line represents learning without explanations, and it essentially outperforms the rest of the models across all conditions. This led us to wonder why explanations did not help. Therefore, we ran 2 analyses on the generated explanations. The first 2 figures here show the hallucination rate of generated explanations under different test scenarios. To our surprise, the BERT model hallucinates names and locations more than half of the time, even for the IND vocab test cases, and the hallucination rate can be as high as 99% when the test vocabulary is out of distribution. We also look at how often the phrase "we do not know" is generated when it's given in the ground truth explanation. We choose this phrase because it is a good label indicator for the non-entailment class. And we see the recall rate to be around 70 to 80% for the BERT model, and it decreases as test instances become harder. So it is not always generated when it should be. Moreover, it is possible for models to generate explanations using the correct entities but the wrong templates, and we include an example here. In conclusion, Although our results show learning from explanations does not help for OOD generalization, we believe explanations contain valuable information, and it is important for future models to learn it more effectively. Thank you for watching, and feel free to reach out if you have any questions or suggestions.